you mean you can't find them? God damn it, Gladys, I need those test results and I need them now! Oh, hi there. Sorry about that. Welcome to this week's episode of
Ooh, science!
And this week we'll be talking to Dr. David Norman, who is the nucleic acid researcher here at the University of Dundee. We've been lucky enough to get an interview with him. So, hello there. This week we're talking to Dr. David Norman, who is the he was a reader in structural biology and a specialist in nucleic acid structural research here. We're talking to you today about your paper on the Holiday Junction. So Dr. David Norman, you published this paper in 2011. How has your research developed since then?
Well, as far as this is the paper describing the interaction of endonuclease 1 with the Holiday Junction.
Yeah.
As far as that's concerned, it's proceeded on from there. We made certain observations in the first paper, especially concerning the N-terminus of the protein, which led us to think that we could use the technique of EPR to investigate what was happening right at the beginning of the protein, because it's an area that we don't know anything about in terms of the structure, because it's the crystal structure, and there are several crystal structures, and although they've been crystallized with and without the DNA, the first 16 amino acids don't show up. Now, you might think that's just because they're inconsequential, they're just flapping around, but at the same time, we know that if you take off those first 16 amino acids, or indeed if you mutate them in certain ways, you do quite dramatically affect the mechanism of the enzyme. So we've got a bit of a mystery which we sort of came to through that first paper, and that is that these first 16 amino acids are both inconsequential as far as structure, apparently, and yet functionally important. And it's that gap which I think we could fill using some of the methods that I use, and that's what we've been doing.
Yeah, fantastic. What's the most drastic change in technology been, and how has it helped your research in this field?
Well, the technology in EPR, EPR is electron paramagnetic resonance, which is a bit like NMR, but it works on the unpaired electron rather than the nucleus. And although EPR itself is a slightly older technique than NMR, it didn't progress as fast, largely because of the technology that was needed. And the technology you need is the ability to make very short, very, very short pulses of radiation. In EPR, it's microwave radiation. In NMR, it's radio waves. And the technology really just didn't exist to make these pulses until not many years ago. And commercially, we here, that's here and in St Andrews, because I work with people in St Andrews, we bought the first available commercial machine for doing pulsed EPR in this country, and we've also built a very high-powered, very advanced machine over there. So that was really the technology change that led me into using this technique, and since then, recently we've got some more money from the Wellcome Trust to upgrade our machine to what they call Q-band, which is an intermediate frequency between the X-band that we use for this paper and the W-band, which is the experimental high-frequency machine we've got over there. And this Q-band is quite interesting, and we've got some money from the Wellcome Trust, and we're hoping to take delivery actually in about 2 weeks' time of Q-band, which is a higher frequency, much higher power. So that will enable us to get the same sort of results, but in either a much shorter time, or more importantly, on a much more dilute sample.
So your area of expertise lies in magnetic resonance. In the paper you've used EPR. Would you be able to explain in layman's terms for our viewers exactly what that is?
Well, EPR is a little bit like NMR, if you know what NMR is, which works on nuclei. EPR works on the lone unpaired electrons, and normally in a molecule, electrons come around as pairs, and they have spin, one spins one way, one spins the other way, and they kind of cancel out.
you can get these species that have a single electron, or radicals, and we use stable radicals, unlike the radicals that are generated by UV light on your skin, which are unstable and very dangerous. These are chemicals which are designed to have these unpaired electrons to be very, very stable. Now, what happens then is when you put these into a magnetic field, the electron will have spin, and it will either spin with the magnetic field or against it, and that's a low energy or a high energy form. And so, like any kind of spectroscopy, when you've got two energy states, you can excite from the lower energy to the higher energy state by putting in energy of the right form, the right frequency. For electrons and the fields we use, it's microwave energy. But the actual, so that's the sort of the basis of it, and you can see the absorption, you get a spectrum. But what we do is we use the spin, the excited spin of the electrons, when you can think of the electron as acting like a little bar magnet. And you know, if you have two magnets and you put them together, as you get close, you can feel the magnetic field. And in fact, not only that, but if you move them around each other, you'll find that the magnetic field is not the same all round, it changes. And that's sort of like what's going on looking at two electrons. So if we put two electrons, attach them onto a protein, and we excite them in a magnetic field, they can feel the effect of each other. And that effect is dependent on how far away they are from each other, the distance, and also, to some extent, on the orientation they are to each other. And we can measure those things in our machines, and that gives us information about distance and orientation of the underlying molecule.
Fantastic. It's a very interesting field. We're going to talk a little bit about the evolutionary aspects of the paper now. The endonuclease enzyme binds into the holiday junction, and this is an important part of DNA recombination. Can you explain to the viewers how this is a vital part of the process?
Well, the recombination involves the swapping over of strands of DNA from two double-stranded DNAs, which happens via a number of different ways, but essentially you get one strand swapping over into another one. And that swap over can actually travel along these two bits of DNA, that's fine, but at the end of the day, you've got to separate the DNA back again. And that's where enzymes like this come into play, because they bind to the region where the strands are swapping over, and they cut them. They make two cuts, and those two cuts essentially separate the DNA back into its two duplexes again. So that's really the role they play in this. If you don't separate the DNA, then it's not going anywhere.
From your results, you've clearly shown through EPR that a conformation change in the endonuclease enzyme occurs upon binding to the holiday junction. How important is the discovery?
Well, the discovery in that paper was in some ways largely confirming the observations made from other forms, which is always very important to be able to confirm if you get a crystal structure, it tells you a lot, but in many cases you do need confirmation that what you've seen and interpreted is correct. So in many ways it was just a confirmation of observations that have been made through other techniques. In other ways we extended that observation somewhat, and as I've described it leads on to other things. So actually, in some ways, the importance of that paper, I think, is going to be not what's in the paper as such, but what it leads on to.
So in terms of the other techniques that you used previous to EPR, what kind of techniques were they?
Oh, well, you mean on this paper in particular?
Yeah.
Well, I mean, there's been crystallography done. I wasn't involved in the crystallography of this before, but there was crystallography done. It's too big for NMR to use on it, or at least it was too big. Maybe we could now, I don't know. I don't know what else. Other techniques have been used, like chemical probing, things like this.
how will your research go on and affect your peers in terms of research into the holiday luncheon and the endonuclease enzyme?
Well, this paper's already led to 2 fourth-year undergraduate projects. One's completed and one's going on at the moment. And I think we'll have some more information. Well, we have got more information, so I think it's going to lead to another publication, probably early next year, concerning the first 16 residues, which turn out to be what's sometimes described as intrinsically disordered, which is kind of nice because it takes us into a new area, an area of protein structure where the protein in some circumstances has no structure, but when it's interacting with another protein, it takes on board a structure. So I think this is it's led us into a very interesting place, and so I anticipate that this will go on, not necessarily on endonuclease 1, but on other systems which have similar kind of circumstances.
And obviously this is all done here at Dundee and between St Andrews as well. In terms of sort of worldwide reach, how big is Dundee in this sort of field?
Well, in EPR we're internationally competitive. I would say that we've probably got the best EPR grouping, or one of the best. Let's be modest, one of the best in the country, and we easily compete with our colleagues in places like Germany, which has got a much longer established research in this area, and also in the United States. So yeah, we're doing very well.
That's fantastic. That's been David Norman.
Thank you.
So that's all from us here at the Sean Connery Seminar Room. We hope you've enjoyed this week's episode of
Ooh, science.
Come back to us next week. Thank you very much.
Ooh,
Science is what we're doing.
That's it, is it? Okay, lovely, lovely.